Imagine you're in a crowded room and need to send a private message to someone across the room. The only way to communicate is by shouting. That's basically what happens on a wireless LAN. Unlike wired networks where signals stay inside cables, wireless signals broadcast through the air, and anyone with a receiver within range can pick them up. Security matters on every network, but wireless demands even more attention because the medium itself is unbounded. In this chapter, we're covering CCNA exam topic 5.9, describing wireless security protocols, WPA, WPA2, and WPA3. We'll start with the fundamental security concepts, then trace how wireless security evolved from the broken original standard to today's protections. The same CIA triad from network security applies to wireless, but each goal gets harder. Confidentiality. In a wired LAN, cables contain the signals. Wireless, every packet flies through the air, so encryption isn't optional, it's mandatory. Even inside your own private LAN, an attacker sitting in the parking lot can capture your traffic. Integrity. Even encrypted messages can be tampered with. A bit flipping attack changes zeros to ones in the ciphertext, creating predictable changes in the decrypted plaintext, without ever decrypting it. The defense is checksums. The sender calculates a checksum, appends it to the message before encrypting, and the receiver recalculates and compares. Mismatch means the message was altered. Availability, wireless denial of service, is embarrassingly simple. An RF jamming attack just floods the 802.11 frequency bands with noise. No hacking skills needed, just a signal generator. The only fix is finding and removing the jamming device, and the only prevention is physical security. The original 802.11 standard defined Wired Equivalent Privacy, WEP. The name promised privacy equivalent to wired networks. It failed completely. WEP had two authentication methods. Open system authentication. The client sends a request, the AP says yes, and that's it. No credentials exchanged at all. Shared key authentication was slightly more involved. The AP sends an unencrypted challenge phrase, the client encrypts it with the shared WEP key, sends it back, and the AP decrypts and compares. The problem? The challenge phrase is sent in clear text, and the same WEP key can be extracted from it. For encryption, WEP uses RC4 with a static key, either 40-bit or 104-bit, combined with a random 24-bit initialization vector. That IV is tiny, and with enough captured packets, attackers can reconstruct the key. WEP's integrity check, called ICV, is also weak. One so create is completely obsolete, but understanding it is crucial because every modern wireless security protocol was designed to fix what WEP got wrong. After WEP fell apart, the Wi-Fi Alliance created WPA as an interim fix. WPA Personal is what you use at home, a pre-shared key, or PSK. Instead of entering a 64-character hexadecimal string, you type an 8 to 63-character passphrase, and the system converts it into a 256-bit PSK. Here's the flow. The client first does open system authentication and associates with the AP, then a four-way handshake confirms both sides have the same PSK and generates unique encryption keys for that session. In WPA and WPA2, this works well. But if an attacker captures the four-way handshake, they can brute force the PSK offline. WPA3 fixes this with SAE, simultaneous authentication of equals. SAE runs before association, still uses a PSK, but the authentication process makes brute force attacks practically infeasible. Both sides verify they share the same key without ever exposing anything an attacker can exploit. For the CCNA exam, the key distinction is WPA and WPA2 use PSK with a four-way handshake, while WPA3 replaces that with SAE. Shared passwords have a fundamental problem. If one person's credentials are compromised, everyone's at risk. WPA Enterprise solves this by authenticating each user individually, using 802.1x and EAP. 3 roles. The supplicant is the client device trying to connect. The authenticator is the access point, or the wireless LAN controller in a split MAC architecture. And the authentication server, usually a radius server, verifies the credentials. The client associates with the AP using open system authentication, but can't communicate yet. EAP messages flow between the supplicant and authenticator using EAPOL, that's EAP over LANs, and between the authenticator and the radius server using radius. EAP itself is a framework supporting multiple authentication methods. LEAP is legacy and insecure. EAP Fast creates a TLS tunnel using a shared protected access credential. PEEP uses a server certificate to establish a TLS tunnel, then exchanges user credentials inside it. EAP TLS is the most secure. Both server and client have certificates for mutual authentication, but managing client certificates can be burdensome. After any EAP method succeeds, the same four-way handshake generates the encryption keys. When WEP's vulnerabilities were discovered, there was a practical problem. Millions of devices were already built with WEP hardware. The IEEE needed time to develop 802.811i, so the Wi-Fi Alliance created TKIP as an emergency patch for the first WPA certification. TKIP's main innovation is per-packet key mixing. Instead of one static key for all packets, it generates a unique encryption key for each packet, making brute force attacks much harder. TKIP also replaces WEP's weak ICV with a stronger message integrity check, or MIC, and adds sequence numbers to each frame to prevent replay attacks, where an attacker captures valid messages and retransmits them later. But TKIP still uses the RC4 encryption algorithm underneath, so it was always a stopgap. It bought time until a proper replacement arrived. The permanent solution arrived with IEEE 802.11i, which became the foundation of WPA2. CCMP, Counter Mode with Cipher Block Chaining Message Authentication Code Protocol, handles both encryption and integrity. The encryption part uses AES in counter mode. Instead of RC4, AES is a fundamentally stronger algorithm. Counter mode works by encrypting a counter value that increments for each block of data, ensuring every block is encrypted with a unique key. The integrity part uses CBC MAC, Cipher Block Chaining Message Authentication Code, which provides a much more robust checksum than TKIP's MIC. CCMP uses a 128-bit AES key and became the gold standard for wireless security. WPA2 is still widely deployed in enterprise and SOHO networks today, though the industry is gradually moving to WPA3. WPA3 introduces GCMP, Galois/Counter Mode Protocol, as an improved version of CCMP. Like CCMP, GCMP uses AES counter mode encryption, but it supports longer key lengths, 128-bit or 256-bit, compared to CCMP's 128-bit only. For integrity, GCMP uses GMAC, Galois Message Authentication Code, which is more secure than CCMP's CBC MAC. The Galois is pronounced Galois, named after a French mathematician. GCMP isn't just more secure, it's also more efficient, which matters because the latest 802.11 standards push much higher data rates, and the encryption protocol needs to keep up without becoming a bottleneck. Let's put it all together. WPA, the first generation, uses PSK with a four-way handshake for authentication, TKIP with RC4 for encryption, and MIC for integrity. WPA2 keeps the same PSK authentication but upgrades to CCMP with AES encryption and CBC MAC for integrity. WPA3 replaces the PSK handshake with SAE for authentication, uses GCMP with AES for encryption, and GMAC for integrity. WPA3 also adds two important features: Protected Management Frames, or PMF, which ensures the authenticity of management frames, like authentication and association messages. PMF was optional in WPA2, but mandatory in WPA3. And forward secrecy, which means even if the PSK is compromised later, past communications can't be decrypted, because each session uses unique keys. As of 2020, a device must support WPA3 to earn Wi-Fi certified status. Wireless security evolved because the medium itself is insecure. Signals broadcast through air, and anyone nearby can capture them. WPA2 brought the real solution with CCMP and AES encryption. WPA introduced TKIP as an emergency fix with per-packet key mixing. WPA2 brought the real solution with CCMP and AES encryption. Du tin Sri Tom. Work continue. WPA3 is the current standard with SAE authentication that resists brute force attacks, GCMP encryption with longer key support, mandatory protected management frames, and forward secrecy. For the CCNA exam, focus on the progression. Which authentication method goes with which WPA version? Which encryption protocol belongs to which generation? And the difference between WPA Personal's shared PSK and WPA Enterprise's individual 802.1x authentication. That's wireless LAN security from WEP to WPA3.